Welcome to this lecture, and this lecture is our lecture that is focused on developing a cancer diagnosis tool. So, what we mean by cancer diagnosis tool and how is it really helping or aiding a clinician to diagnose the cancer in a better way than the current existing tools. So, we are talking about tissue related cancers, all right. And when we talk about tissue related cancers, there are several cancers which are tissue related cancer, and amongst those we will be focusing on breast cancer. So, let us see what we are talking about, and at the end of this course, at the end of this particular lecture, you will be able to fabricate or at least understand the process flow for fabricating a biochip that can measure certain properties of tissue which can lead to a particular diagnosis. All right. So, if we see the slide for this particular course, right, we are talking about cancer diagnosis tool. So, we will be developing a tool, right, that can measure multi-parameter of tissue. What are multi-parameters? Multi-parameters can be stiffness of tissue, right, or in another way mechanical properties of tissue, right, mechanical properties of tissue. Then we will measuring resistance of the tissue, or in another way we are measuring electrical property of tissue, electrical properties of tissue, right. Third, we will be measuring the change in the temperature of the tissue when we heat the tissue from the bottom. So, if I place a tissue on a heater and I keep it at 37 degree centigrade to 40 degree centigrade, I keep a thermistor here and I measure the temperature at the top surface. Let us say this is T2, this is T1, right, and I see that how much is a variation between T2 and T1, and from that what we are measuring? We are measuring the thermal conductivity of tissue. Thermal conductivity of tissue, right, or in one sentence it is we are measuring that we are measuring mechanical, electrical and thermal properties of tissue. This is what I mean by multi-parameter, all right, measuring the electrical property, mechanical property and thermal property of tissue in one go is a multi-parameter diagnostic device. Now, another point is, so if I just rub it off, another point is that this diagnostic tool should be portable. That means, I can take it to from one dispensary to another dispensary or from one hospital setting to another hospital setting without any problem, right. And what is the use of this? So, what are the gold standards that are used in diagnosing cancer? Right now, let us say a patient is suffering from a breast cancer. What are the parameters how a person would know, right. The first thing is self testing. Look at the abnormality in the breast, look at the leaky fluids, all right. But what else we need to do, right, and why we have to test the electrical property, mechanical property, thermal property of tissues, right. So, let us see, first let us understand the breast anatomy, right, and see, even we are designing a microengineering device or microengineering or biochips which can be used for cancer diagnosis. It is very important to first understand what cancer we are targeting, and if we are targeting a breast cancer, we should know, right, what is the anatomy of breast. Otherwise, it is very difficult for us to directly start fabricating the device. So, if you see the anatomy of breast, what we see that there is breast consists of ducts, right, it consists of duct, then it consists of lobes, it consists of fat, right, duct, lobes and fat. This is fatty tissue here, then these are lobular tissues, this one, and then finally there is a duct, right. So, and this whole thing is supported by pectoral muscles, right. This is the anatomy of a breast, just not to go in detail. So, three things we understand. First thing is that it consists of duct, it consists of lobes, it consists of fat, and the breast is supported by pectoral muscles. Right. This much we understand. Now, if the breast if the cancer happens in duct, then it is called ductal cancer, right. In the case of breast cancer, if the cancer occurs in duct, it is ductal cancer. If it happens in lobes, lobular cancer. It happens in both duct and lobes, it is called multi-tumor breast cancer. Then if there is a inflammation, it is a inflammatory breast cancer, and if there is a mucus, is mucinous breast cancer. So, types of breast cancers are there, right, and it is very important to understand this, because breast cancer is second largest cause of cancer related death in women. Very important disease to understand, and thus it is very important to diagnose this particular cancer in early stage. In fact, diagnosing any cancer in early stage will double the chances of survival than diagnosing at a later stage, or in fact triple the chances of survival. All right. So, as you can see, there is a tumor formation in the breast, right, and that is what we call as cancer. All right. Now, there are two types of further cancer. One is called non-invasive. Second is called invasive. What is invasive and what is non-invasive? So, when there is a tumor and the cells comes out of the tumor and moves to other part of the body, through lymph node. We all have lymph nodes, okay. Lymph nodes are used to activate or to protect or to enhance our immune system. Lymph nodes are used or are the part of our immune system, to make it simpler. And the cells, when they are not localized, if they stay there, if the tumor says their cell stays there, it is non invasive, it is not invading other part of the body. But if the cells moves from the present location to another part of the body through lymph nodes, it is called invasive kind of breast cancer, invasive breast cancer, right. So, what we understand, breast cancer two types, one is invasive, one is non invasive. Then we understood that based on the area of the breast, it can be further classified as ductal cancer or lobular cancer. If it is in duct and lobe both, mixed tumor cancer. If it is mucinous, mucinous cancer. If it is inflammatory, inflammatory cancer, right, this much we understood. So, now what are the gold standards, how it is diagnosed currently? So, there is a technique which is called mammography. What is called mammography? So, let us see the next slide. Let us see the next slide. So, if you see breast cancer statistics, what it says that according to World Health Organization, last report of it, right, cancer remains a global problem. Around 14.1 million new cases arises, right, or were diagnosed in 2012, out of which 8.2 million people died, right. And again, it is very difficult to understand how cancer happens, what is the root cause of cancer, difficult. There are a lot of theories, but there are a lot of speculations and theories, but not a certain answer why it happens, what to do to stop it, what to do to prevent it, right. We all learn that prevention is better than cure, or precaution is better than cure, precaution is better than cure, right. So, how I can be cautioned that I should not do this, so that I will not have a cancer, right. So, what I studied or what I found from the literature is that if you avoid processed foods, if you avoid foods that are modified, genetically modified, keep it, we keep our body cleaner, right, compared by when I say cleaner, it is not just taking bath, but also what food we consume. Are we consuming all the processed foods, right, are we consuming all the genetically modified foods or fruits or vegetables? If so, we should not, right. So, again what I am telling is from my reading, my experience, right, and what I will tell is avoid any processed food, eat clean food is easier, all right. Fortunately, as per my understanding, within our country, right, still there is no genetically modified food. The grains that are grown, the fruits that are grown, the vegetables that are grown are not genetically modified. Of course, there are use of pesticides, but not genetically modified, right, except cotton. Cotton is genetically modified, and that is why there is a huge amount of cotton. We can export cotton now, right. When you modify a fruit or a vegetable or a grain, right, genetically, then it will stay for longer time, it is fresh for longer time, it grows faster, it yields faster, the yield of the product is more, right. So, in certain countries when you go, you will find that the fruits are bigger in shape, the flowers are way bigger in shape, right, and it does not stay for a longer time, not just because of the temperature, but because it is genetically modified. Now, how much it affects the body, I do not know. Whether it will cause cancer or not, I cannot say, but is it good to avoid that? Yes, that is the precaution, that is the precaution, right. And in fact, that is why the whole world is running after organic foods. Organic foods, what is organic food? Where we use the organic material to grow our grains, fruits, vegetables, right. Cow dung. If you see how organic pesticides, when you say about chemical pesticides, pesticides in particular, they also harm to a level, not only they just kill insects, but also harm the crops. Of course, when I say harm the crops, does not mean that crop dies, but still it is a chemical. We have to wash the fruit thoroughly, vegetables thoroughly. There may be part of pesticides left in the leaf, suppose you eat spinach, right, but organic way of doing it is much more safer, and that is what we were doing from centuries, right. And there, from someone I heard this story, and in fact it is a real story, that that people were making fun of our forefathers. They are using cow dung, they are using coal and salt for cleaning teeth, right. And now you see MNCs have salt in their toothpaste, right. And the fruits in some of the countries, they are, or fruits and vegetables in some of the countries, when you travel, you will see organic markets. In fact in India also we will now see organic markets, right, and they sell it at much more higher price than the fruits grown by pesticides, right. So, the point that I am making is that try to avoid processed food once in a while, because of our lifestyle we cannot not avoid, and that is fine, right, but try to avoid it. Try to avoid genetically modified food, try to learn what exactly this all things are, it is called GMO. Anyway, so but the point is, you see that there are so many cases, 14.1 million cases, out of which 8.2 million died in 2012. In fact, like I said, if you talk about just breast cancer continues to be second largest cause of cancer related female deaths in world, accounting for 12% amongst all cancer, 12%, very high number, very high number. And Indian Council of Medical Research in 2016 estimated about 14.5 lakh new cancer cases and projected that this is likely to reach 17.3 lakh new cases in 2020, which is not too far. It was also reported that breast cancer constituted an estimation of 1.5 lakh over 10% of all cancer cases in 16, and making it number 1 cancer overall. You see, now there is something even worse, and that is called triple negative breast cancer. What is that? Triple negative. You see here, triple negative breast cancer, also called TNBC, which is an aggressive type of cancer, accounts for about 12% of breast cancer cases, and no specific treatment currently exists for this subset. Now, this is based on the literature which is right over here. I am not making my own statements, these statements are supported by the literature, right. Triple negative breast cancer, aggressive type of breast cancer, 12% of overall breast cancer, and no specific treatment exists for this subset. Specific treatment, it does not mean there is no treatment, but specific for triple negative is not existing. Alright. Now, which are other cancers, tissue related cancers, and why we are talking about this? Because we want to see that if there is a gold standard, and if you see a gold standard, if you see the diagnosis, there is lot of false positive and false negative results. What exactly false positive and false negative results means? That if a patient has a cancer, the report comes at it is okay, you are okay, and if a patient is not having any disease, right, no, he is not suffering from the cancer, the report says that you have cancer. False positive, false negative, right, that false positive, false negative rates are higher. So, if we can design a tool based on our microengineering knowledge and little bit of additive manufacturing, that is your 3D printing, laser cutting, right, engineering designs, you all do engineering drawing in first year of your undergrad, right, you use workshop. So, using this basic knowledge of microengineering, additive manufacturing, can we design a tool that can aid the clinician and reduce the false positive and false negative signals. That is the idea, right, that is the idea. So, when we talk about tissue related cancers other than breast cancers, which are other tissue related cancer. So, let us see that, you see in 2015, according to 2015, right, this is just about United States of America. So, it is the report from American Cancer Society, which says that just in US, estimated cases and estimated deaths, you see estimated cases, estimated death, cancer type, prostate cancer occurs in men, alright, like breast cancer is extremely dangerous for women, prostate cancer is dangerous for men, and 26% is was the estimated cases in 2015 report, and 9% of the out of 26% was the estimated death, was the figure for estimated amount of death or number of deaths. Second one was lung cancer, both in men and women, 14-13 close, death 28 and 26%, out of 14% that is detected, 28% dies and 26% in women. Colon cancer and rectum cancer, 8%, look at the death, 8% and 9%. Urinary bladder, 7% death, from 7% 4% dies. Breast cancer, amongst 29% of estimated cases, 15% from 29% is the death rate. Same way lymphoma, thyroid, leukemia, right, which is blood cancer, melanoma, which is a skin cancer, right, kidney and renal pelvis, and finally uterine corpus. So, these are the major cancer that occurs in humans and estimated death in numbers from this particular table, right. So, when we talk about this, what does exactly the statistics that we were talking about means? That means that worldwide it is estimated that about 1.68 million women were diagnosed with breast cancer in 2015, which means 1 in 8 women will be diagnosed with breast cancer during their lifetime. 1 in 8, right, because it is 1.68 million women were diagnosed with breast cancer in 2015. That means approximately 1 in 8 women will be diagnosed with breast cancer during their lifetime. Second, breast cancer in United States, each year in the USA the more than how much is this, 2,32,714, right, 2,32,714 breast cancers were diagnosed, amongst which 43,909 women died. That means in US for every 5 or 6 women newly diagnosed with breast cancer, 1 is dying. For every 5, 1 is dying. Now, let us talk about our country, right. So, there were about 1,44,937 new cases of breast cancer in India in 2015, amongst which 70,218 women died of breast cancer in India. 70,000, right, the big number, and in general nobody should die, That is what we want, right. Nobody whom we love should die, but the real truth of our life is a death. Nobody can deny it, right. So, the point that I am making is a loss of a family member is a great loss, and that too a woman, because is a pillar of a family. She is a pillar of a family. Man is there, but woman has multiple roles. You see, mother, sister, daughter, right, and that role no man can replace. In fact, it is a great role that only a woman can do. A loss of a woman in a society, a loss of a woman in a family is a great loss, is a great loss. Same stands true for men as well. But my point is, why to lose anyone just because of some disease, and we have the medicine to cure, we have the curing pills, we have the all the tools to cure, but we do not have tools to diagnose it early. It is not that we do not know how to cure, but by the time we know there is something, it is too late. And that is why this engineering design, our understanding of engineering, we can apply to solve and diagnose a cancer. That is why we are learning this particular topic, alright. So, if you see back the statistics in India, for every two women newly diagnosed with breast cancer, one is dying of it. First of all, we are not aware, right. Unfortunately, the awareness program is not reaching to each and every person in the society. Awareness program, we should be aware, right, what happens, how to do self testing, self examining, where to go, what kind of diagnosis we should do, primary health care. And when I am talking about self awareness, you will see in the next slide what I mean by that, But the situation is even worse when we talk about our country, and what is that? For every 2 women newly diagnosed, one is dying. So, if you talk about the awareness, what is awareness? That a woman should go for mammography if she is below 54 every year. Mammography is testing the breast to understand if there is any suspicion region or not. Gold standard. Exactly, I cannot say gold standard, because there is a pathology also involved next to after mammography, where they take the biopsy and they do the IHC and then measure the biomarkers. So, it is not a really gold standard, but it is a standard diagnosis tool. Mammography, women between 40 and 54 or below that, right, every year they should go and do this examination. Do we know that? How many of us knows that? Very few, right. Self awareness or awareness about this disease. When we are aware, we can test, we can diagnose early, we can be healthy, we can live longer. A woman who is above 55 and above, right, every 2 years once she should go and do this testing, right. So, if you see the slide, that is what is written. All adult women of all ages are encouraged to perform breast self exams at least once a month self examination. Like I said, right, stiffness, leaky fluids, inflammation, that is all self examination. And mammography every year 40 to 54, right, women between this age should go every year, in fact less than that should also go every year, and every 2 years 55 and above, right. So, you see, if you go for MRI, if a patient who is suffering from breast cancer and goes to MRI, and you can see in MRI the suspicious region, suspicious region, right. Same way for mammography, you see this is mammography, right, and here you can see the suspicious region, this spot, this white spot that you see is a suspicious region, right. So, what happens once we see that there is suspicious region, or not we, but the clinician looks at the suspicious region, what is the next step? What is the next step? The next step is that the patient is advised for biopsy. Biopsy is when you take out the tissue from the suspicious region. You take out the tissue from the suspicious region. So, when you take out the tissue from this suspicious region, which is your tumor, what next? The next is the tissue is sliced and sent. So, tissue is sent to the pathology lab, path lab, pathology lab, tissue is sent to pathology lab. So, when you do the biopsy, there is a tissue, you can see tissue right over here, and is sent to path lab where it is sliced further. You can see here slicing for immunohistochemistry and spatial staining, IHC and spatial staining, you see here this one, alright. So, when you do this IHC and spatial staining, you are looking for certain biomarkers, and if the biomarkers are present, then the diagnosis would be that okay, the patient is suffering from cancer, or the patient is not suffering from cancer. So, when we talk about biomarkers, what are these biomarkers? The biomarkers are HNE, estrogen, prostrogen, SMA, P63, and one is called HER. These are the biomarkers that the path lab or the pathologist will be looking at. What? HNE, P63 SMA, estrogen biomarkers, prostrogen and HER. Alright, this much is easy, very easy, right? To understand it is easy, but the diagnosis is not so easy, it is difficult. Alright, so now what we want is, can we design a tool, can we design a device that can measure other properties of tissue except biomarkers or the optical way of understanding, which the mammography is also using it. So, here the idea is, can we measure the stiffness of the tissue, that is a mechanical property, can we measure the resistance of the tissue, electrical property, can we measure the thermal property of tissue, that is thermal conductivity of tissue, and to do all three things we need to design now a biochip that can perform all three experiments together, or all three it can detect all three parameters of the tissue, right. So, if we see that, if we see the slide, what we see that the tissue is sliced further and it is given for our experiment, and another tissue is sent for FESEM, it is a scanning electron microscopy. So, if you see a tissue here, if you see the tissue here, now there are two regions, one is a epithelial region, another is stromal region. If the cancer is in stromal region, it is called stromal cancer, epithelial region epithelial cancer. 70% of cases or most of the cases in epithelial region, 70% of cancer, breast cancer is in duct and it is called ductal cancer, right. So, ductal cancer are about 70%, and that is again based on literature. So, if we perform the FESEM, what we see is that the structure of the tissue from normal, and this is IDC, invasive ductal carcinoma, IDC invasive ductal carcinoma. Alright, this is IDC. So, if you see the morphology or the topography using the SEM image, using the SEM, right, what we see? We see that the IDC, which is invasive ductal carcinoma, the tissue is much more ruptured and the normal tissue is smoother compared to, this is smoother compared to this one IDC. This is normal, and this one is cancer, carcinoma. So, when you look at the images, we look at the normal and the carcinoma, then you can see that the normal tissue is smoother and the tissue which has carcinoma is rough or it is ruptured, alright. This is what we see. Now, what we want to do? We want to measure electrothermomechanical phenotyping, or we want to phenotype the breast cancer. So, electrothermomechanical phenotyping of breast cancer, alright. So, let us see what should our biochip consist of. Biochip consists of a bottom layer which is microheater, On this microheater, so you can see here process flow, okay. Look at the process flow here, and then we will see how we can fabricate this thing, that I will show you the process flow in detail. Right now just concentrate on this particular slide, on this particular image. Process flow, first is you take a silicon wafer, this is silicon, alright. Second step is you grow oxide, this is SiO2 on silicon, then you form a microheater. You can see here you deposit a metal, do lithography and form a microheater. Okay. On microheater you again deposit a insulator, SiO2 on microheater, I will say MH just to make it easy. You get it? Where are we right now? Silicon oxide, that is grown on silicon, on which we have, using photolithography we have patterned microheater, okay. And then there is a insulator on microheater. The reason of placing this insulator is that next would be our interdigitated electrodes. You can see here, right, this one, this step, but I cannot directly pattern interdigitated electrodes on microheater, because metal of microheater and metal of interdigitated electrode will get shorted, will get short, electrical short, right. So, to avoid this short, we are depositing or we are growing insulator on the microheater, and then we are forming the, we are depositing gold and pattern it using lithography to obtain interdigitated electrodes. Now, in between there is a step where you open the contact, you do not deposit the material. So, here also there should be a contact like this. You do not deposit or you deposit silicon dioxide, then you perform lithography such that the contact area is open, only the window here you can see red one, that should be open, that means that there silicon dioxide should not be there, otherwise we cannot take contact to the heater, right. So, after this you perform you deposit AU and perform lithography, so that you will obtain this particular step. After this you deposit in this step piezoresistive material, piezoresistive material and pattern it. So, you get this 4 squares, and you can see right over here, okay. After this, after piezoresistor, there is one more step which is not mentioned here, but there is one more step where you again grow after step 6 you take this one and then grow a silicon dioxide, alright. Then you deposit gold and form a pad which is here. On this pad you deposit SU8 and pattern it in form of pillar, and then you make SU8 conductive by using lift off technique. Again, when you do this, you will obtain this. From the back side, if I etch the silicon using bulk micro machining that we have learned early, then I will have, you see I have etched the silicon from back side. So, what will I have? I will have a diaphragm, I will have a diaphragm on which the entire structure is there. So, if you see this particular structure, this one, then below this, below the circle on the back side there is a etching. So, when I press it there will be a bending, right, you get it. So, the front side is the pad. So, here if you see the pad is somewhere like this on the front side, back side there is etching, on that pad this structure is there, right. So, we have etched the silicon from back side using bulk micro machining. So, let us see quickly once again what we have done. What we have done here, we have started with a silicon substrate, right, then we have grown oxide which is number 2, then we have deposited metal for micro heater and patterned the micro heater, then we deposit silicon dioxide which is an insulator and we pattern the insulator such that the contact area is open here. On that we deposit gold and we pattern the gold to form interdigitated electrodes. On interdigital electrodes we deposit piezoresistive material which is 6 number here and pattern it to form these squares. On that we have an insulating material on which we have a gold pad and gold pad is patterned, on which there is an SU8, there are SU8 pillars and these SU8 pillars are made conductive using lift off technique which is number 9, and on the back side we etch the silicon to create a diaphragm to obtain finally this particular design, right, and the chip is right over here, chip is right over here. So, what is the use of this, right, what is the use of this, we should know what is the use of this. Let us say what is the use of this. We have now 3 things, if you have noticed we have 3 things. What? First is I have a heater, second thing I have a piezoresistors, third thing I have a electrode. You see this one, this is a electrode. If you see this one, let us say electrode 2, just we are just giving a name, or let us say electrode 1. This electrode 1 consists of 4 SU8 pillars on gold pad and this everything is conductive and this gold pad is connected externally. So, that from here we can apply or we have one point which is our electrode 1, one contact pad for electrode 1. 3 things we have, right, heater, piezoresistor, electrode. Now, let us see how we will use this one and where we will place this thing. So, see this structure and look at this structure in particular first. What is it? It is an rod, right, that has conductive rod, sorry, conductive rod, and it has a thermistor and this is conductive. So, it can be our electrode number 2. There is a thermistor here and it is conductive, right. So, this is our indenter. What do we say? Indenter. Indenter is used to indent, like let us say if I have a material or I have a tissue, this can press it, this can indent it, indenter, alright. Conductive electrode because it is a conductive and we have thermistor at the tip of the indenter. Understood this much? Now, what we will do? So, we will design a case using 3D printing such that this case consists of top part which is right over here, you can see this particular portion. It consists of top part, right, and in the top there is a rubber packing, then there is a press fit contact pins, then there is a middle part then there is a microchip or biochip, then there is a spring, then there is a bottom part, and then there are alignment columns, right. What is that? Let us see once again. Top part, press fit context, middle part, microchip or biochip, spring, bottom part, and alignment columns. Okay. This much we have. Now, what we will do? If I press fit everything, if I bring everything together, if I bring this whole structure together, it will look like this. You get it? If I press this structure together, what it will look like? It will look like the one that I have shown it to you here, which is this particular structure. You can see spring, you can see 12 pin connector, you can see the biochip within it, right. You can see the biochip, see 12 pin connector biochip, there is a spring, and then there is a conical flask like thing here, right. Here you can see here the top part we have created this structure. So, what exactly we have done? Here we have made a 3D printed case such that it consists of, or it is integrated with a microchip. There are no shoulder, no shoulder wires. There is no soldering. There is no wire bonding. No soldering, no wire bonding. But there is a press fit contact. Press fit contacts. Right. This particular design is such a design that it makes our life so easy. We do not have to do soldering, we do not have to go for wire bonding, and we just have to load our chip within this 3D printed case, and we press fit it. Because of the press fit contacts, we can take out the signal, or we can measure the signal from the external pins directly. One thing, one advantage. Second is that now you can load the tissue. You can load the tissue in this particular section, and this tissue, when you press fit everything, this tissue will, you can see this funnel going all the way around, like if I draw here, it goes all the way around like this, right. And where does it end? It ends in the center of the biochip. It ends in the center of the biochip. That means, if I load the tissue here, right, I bring the tissue down, right. So, what will happen? Finally, the tissue will be placed on the biochip. You get it? The tissue will be placed on the biochip. So, if I place the tissue, you can see this funnel, right, funnel, and at the bottom of the funnel there is this center of the tissue is there, this one. So, the tissue is placed directly in the center of the biochip using this particular mechanism, all right. You got it? So, if I place the tissue like this, and if I place this indenter, so there is a tissue, let us say this is a tissue on the biochip, and now what I am doing? I am using an indenter, this indenter, which is our electrode 2, right, and on the biochip, on this biochip, what we have? We have electrode 1, right. Let us see back, we have this electrode 1. So, if I apply voltage between electrode 1 and electrode 2, then the current will pass through the tissue, right, based on the tissue resistance. You get it? If I have electrode 1 on biochip, electrode 2 is on indenter. If I press it, if I apply voltage between E1 and E2, then the current will pass through the tissue based on the tissue resistance, and that is why I can measure the resistance of the tissue. I can measure the resistance of the tissue. One thing. Second, if I press this indenter, if I press this indenter, if I indent the tissue down, then the tissue will the force exerted by this indenter will be transferred to the piezoresistors via tissue, right. If I indent this indenter in this direction, with a particular amount of force in micro nanonewton. This force will be transferred to the biochip, and the biochip has piezoresistors. So, how much force will transfer to biochip? Based on the stiffness of the tissue. So, the amount of force applied and amount of force transferred to the biochip, that will help us to determine what is the elasticity of the tissue or stiffness of the tissue, right. If the tissue is stiff, then the amount of force will be different. If tissue is smoother, if tissue is less stiff, sorry, not smoother, less stiff, if the tissue is less stiff, then the amount of force transferred would be different, right. So, now we can measure the mechanical properties of tissue. You got it? Two things you got it, right. Third thing, what is there here? Thermistor. What is our what our biochip consists of? Our biochip consists of heater, right. So, now if I heat the tissue from the bottom of the tissue, I heat it with the help of the heater, which is integrated on my biochip, and let us say the temperature is 40 degree centigrade. I can measure the top surface of the temperature at the top surface of the tissue. I see the bottom surface has 40 degree. I can measure the temperature at the top surface of the tissue with the help of thermistor, So, now I have T1, which is, let us say T1 is 40, and with the help of thermistor T2, right. From this, since I know the temperature at the bottom surface, the amount of temperature at the top surface. So, if there is a temperature difference, and based on that I can measure the thermal conductivity of the tissue, or I can measure thermal properties of tissue or thermal conductivity of tissue. You get it? So, now if I place the tissue, in this particular setup, I can measure the mechanical, electrical, which is resistance, and thermal properties of tissue. Cool. So, what will I do with this if I can measure electrical, thermal, mechanical properties of tissue, and how it is really helpful, right, how it is really helpful. So, let us see. First of all, when we measure electrical property and thermal property, is it different? My point was that if we develop this biochip and we measure the electrical, thermal and mechanical properties of tissue, are the electrical, thermal and mechanical properties of normal tissue different than cancer tissue, right. Are the electrical, thermal and mechanical properties of normal tissue different than cancer tissue, and if there are difference, then we can understand that the tissue is changing its property, the disease is progressing, and we can diagnose the change in the tissue property, and thus we can diagnose the cancer possibly at earlier stage, right. So, but can we understand the signature? Can we understand the signature of the tissue or properties that is changing in the tissue? So, for that let us see the result. So, what we see here again is, so one way is that you take the live biopsy, means when you take the biopsy is when you take the tissue from the suspicious region out, right, and directly place the tissue onto this system, onto this tool, or you can save this tissue in this tissue bank, right, which is using the paraffin block. This is a standard way of storing the tissue in a tissue bank, and whenever you want to use it, whenever you want to test it, you can deparaffinize tissue, means you remove the paraffin, right, take the tissue out and place the tissue on this device, on this tool. You see here is a deparaffinized tissue, this white one, deparaffinized tissue. This is paraffinized tissue, all right. So, that is one thing. Now, when we measure the normal tissues and cancerous tissues, in here we have taken case of invasive ductal carcinoma or IDC. That is why you can see here IDC, all right, IDC. So, we have used invasive ductal carcinoma or IDC, and with the help of indenter, when we indent the tissue with depth of indentation, with the depth of indentation in micrometers, we could see the compression force, and we can clearly see that the force obtained, the compression force obtained from normal tissues is different than cancerous tissue, is different than carcinoma. Second, the resistivity of the normal tissues is different than the resistivity of the cancerous tissues. Third, the thermal conductivity, you can see this these 3 lines here. The thermal conductivity of cancerous tissues is different than thermal conductivity of normal tissues. What we see that there is all 3 properties changes, in fact when you see the normal tissues and take the SEM, you take the cancerous tissues and you take SEM, you will see that the cancerous tissues shows much more ruptured structures. What is rupturing, what is not smooth? When something is not smooth, the resistance would increase. Where resistance is increasing, the thermal conductivity also would be different, right, and that is what we have measured here, So, if you see that from mechanical, electrical and thermal property of tissues, we can get a sense that when we will be measuring lot of samples, we would have a particular signature that will help us to diagnose whether there is cancer or not, or you can diagnose cancer in fact in a earlier stage, right, because the properties of tissue would be different as the disease progresses, all right. And all the things that I am talking about is from the publication IEEE Transactions on Biomedical Engineering, which was published earlier in 2016 or 16 probably, and these are all the results that is from the same publication. So, if you want to just go back and see this paper towards a portable diagnosis tool using a disposable MEMS based chip from IEEE TBME, you can go, you can read in detail what exactly we have done. IEEE Transactions on Biomedical Engineering. Okay. So, now the point is, if we know these things, now if we know that we need to fabricate the biochip, right, we need to fabricate a biochip which will have the heater, which will have piezoresistors and which will have electrodes. Then we have seen here process flow, but let us now see how we can fabricate each of this component, each of this sensor on the biochip, all right. So, in the next module, we will be looking at each of these sensors that we can fabricate on a biochip, right, from heater, then interdigital electrodes, over which there is a piezoresistor, over which there is a electrode, on which there are SU8 pillars, on which we are making SU8 pillars conductive because SU8 is a polymer, non-conductive polymer, and finally we are creating a diaphragm by etching the silicon from the back side, right, bulk micro machining. So, we will see in the next module the fabrication or the process flow for fabricating this biochip. What I will like you to do is go through this module once again, also read about types of cancer, read about breast cancer. In fact, when you go to YouTube and write down breast cancer and its stages, breast cancer and its stages, you will be able to understand thoroughly or slightly better how exactly the cancer progresses and what are the stages of cancer. Then by understanding that, you may get more problems, and probably with that problems you may have more solutions, and the solutions can be or may be based on the knowledge that we are acquiring by understanding the microengineering. Right? Can you come up with a new device, a novel device, a better device than what I am showing it to you? That is the idea. The idea of discussing and exchanging the viewpoints, the knowledge is that we increase, we make our research better. We come up with new ideas, new technologies that can be better than the existing one or what I am performing on. Whatever I am doing is what I know. Can you come up with a better solution than what I know? Then it is worth of talking and discussing and understanding the microengineering, right. That is the idea. So, think about it, read and learn these videos once again, go through this module once again, and in the next module let us see how we can draw a process flow, what should be the recipe so that we can fabricate this biochip. All right. Till then, you take care. I will see you in next module.